Hi, let's start. Today we're going to learn how to solve inhomogeneous linear system ODE. Remember last lesson we solved the homogeneous linear system ODE, and I was going to give you the outline first, then I will show you what's the difference between inhomogeneous and homogeneous. So first I'm going to introduce what is an inhomogeneous linear ODE and a theorem about a superposition principle. And then we're going to use a variation method to solve the system. And finally, I'm going to show you the maple commands to solve the system. Back to the example I showed you before. There's two tanks. They're connected like this. Let me draw it right. And these two connected tank A and B have the fluids going this way and then go to here, the fluid back, and then this flow out. Remember that example. In that example, in last lesson, it's a homogeneous system because all you have is the equation like this. Well, the A is this coefficient matrix. But if I do a little bit of change, in the process add another pipe here and here to input some pure salt in different time as a function like this. You know, you can do the calculation. When t equals 0, you add 1/4 pound into the tank, and 1/3 to the second tank. So if we add this term in the end, and then you have a different system. And this system not only includes this first degree of x, but also include a we call it inhomogeneous term. In other example, if I give you a spring mass system, and this really stands for external force, we're going to see next hour. So the difference of this equation, if I want to write it out completely, is this. x1, x2 equals negative 1/3, 1/12, and negative 1/3 of x1, x2 plus, let me change the color, and plus this. We call the inhomogeneous term, e to the negative t over 4, e to the negative t over 3. I leave this system as your exercise for today. So in general, if we want to write a system of n variables and n equations, the n could be 3, 4, 10, any number. In the previous example, n equal 2, just to make it easier, we typically focus on only n equal 2, 3, at the most 4. In our handwriting, the real difference is this. You add this term. That's the inhomogeneous term. And then the system, if you let the x vector equals x1, x2, xn, they are all functions of t, and let the A equals this coefficient matrix A11, A21. This we did many times. And the AN1, that's a square matrix. ANN, we call this as a coefficient matrix. And then this B equals this vector here. And then your system look exactly the same thing like the previous one. X derivative equal A times X plus B. And those are functions of t. So yesterday, you learned, not yesterday, last lesson, you learned how to solve this. And this lesson, our goal is to solve this sometimes with an initial condition too. So this system, we call it initial value problem of inhomogeneous linear system, ODE in short. So this is our goal for this lesson. The first theorem is a good news for existence and uniqueness. If you have such a linear system and you have the initial condition, the solution is guaranteed, is unique. That's a perfect situation in the real world application. You want a solution, you want a single correct solution. The emphasis for this is linear. Without linearity, I can give you many examples. Either you don't have a solution or you have many solutions in an initial value problem. So first theorem is just to say you're worry-free. At the worst, we can get a numerical solution, do approximation. But today our focus is analytic solution. The next theorem, when we talk about the superposition principle, show you how we are going to solve this system. And the superposition principle show you if this is the n linearly independent solution to the homogeneous system. We call it associated homogeneous system by dropping off this BT. See, we don't have BT, and this is homogeneous. And we know how to do that on last lesson. And when you put this together, you remember we call it XH, a fundamental solutions matrix. That's what we learned in last lesson. If you get this one, and you also find the one particular solution, you just need the one for the inhomogeneous. This one is for this. You find the one for this. And then add this one, we call it a particular solution. This is called a particular solution. XP, the little p stands for particular, the little h stands for homogeneous. And then your solution is a general solution. We call this as a general solution, right? To the homogeneous equation, plus a particular solution, then we got all general solution. So once you get your general solution, you can figure out those constants, C1, C2, Cn, by use the initial condition. So now, it's very clear to solve such a system, you have 3 steps. Step 1, you need to solve the homogeneous system as we did in last lesson. Step 2, we need to find one single particular solution. Even you have infinite many, I only need one. And step 3, you figure out these constants if you have the initial condition. So we're going to see a few examples today. Now, the first example, this is the second example. All I need to show you is how does the solution look like. And we have this system. This is inhomogeneous because I have this extra term, bt. This is my bt. And the solution have two components. First, this 3 is the solution to this homogeneous equation system. That's the 3 homogeneous solution. And put these 3 together, and this one, we call it fundamental solution set, solution matrix. To qualify this as a fundamental solution matrix, you need to do 2 jobs. What is the 2 thing? Now I said that this is verify. You need to take this derivative and on the left, then multiply this to the matrix to see if this is a solution. You need to do the check. We did this last lesson. You need to do the same thing for this second. Take the derivative. Let me just quickly do the second. The second, you take the derivative, that's e to the negative t. That's not a real change. And on the left, the right, multiply this to this matrix. What you get? You should get exactly the same. And then you say, okay, here's a solution, here's a solution. Now you finish the check, you say, I got 3 solutions, I'm done. No, not necessary. You finish this 3, another keyword is independent. What it means independent? You remember the round skin. You need to check the round skin. Take 1 point here, let t equal 0. If t equals 0, that's negative 214. See, negative 214. And you look at this determinant. If the determinant is not 0, you are really good. The 3 solutions are linearly independent. So you got 3 solutions, you got 3 linearly independent, bingo. Now you got this fundamental solution matrix. That's step 1. Step 2, what else you need? You need a particular solution. What is that? Oh, this is a particular solution. That's my XPT. And you can check. So when you check this solution, what you need to do? You need to go back to the original equation and make sure the left take a derivative, multiply, you got this, negative 722. And that's important. So once you get the one particular solution and the one general solution, you add, you can write it down this way, or you can write it down this way. They are the same. That's up to you. So that only gives you a so-called general solution. So how do you get the C1, C2, C3? Now, if I know my x is 0, let's say equal 1, 2, 3, and then you let the t equal 0, you can get this C1, C2, C3.